The modern electrical grid relies on generating massive amounts of energy at a single, centralized location, like a large-scale hydroelectric dam. Deep inside these facilities, mechanical energy is converted into electrical energy by a synchronous generator. A standard unit outputs 200 megavolt amperes at 11 kilovolts. This equation illustrates our core infrastructure problem. Transmitting that raw power requires a current exceeding 10.49 kiloamperes. But every conductor has a thermal limit defined by I squared R. Forcing 10,000 amps through standard grid wiring will rapidly melt the copper. Direct, long-distance transmission of a generator's raw output is physically impossible. The grid requires a mechanism to bypass this thermal boundary. The engineering solution is the power transformer. This static device manipulates the ratio of voltage to current without altering the AC frequency. By stepping the generator's output up to a high transmission level, like 440 kilovolts, the required current drops proportionately, making long-distance transit entirely viable. To understand how power teleports between disconnected circuits, we analyze the ideal transformer. We define this model with three strict traits: infinite core permeability, absolutely zero leakage flux, and zero thermal or eddy current losses. By stripping away real-world inefficiencies, we isolate the pure magnetic laws governing the transfer of energy. To predict how a transformer manipulates voltage, engineers mathematically map the familiar logic of electric circuits directly onto solid magnetic cores. In standard electrical circuits, voltage drives current against physical resistance. The magnetic circuit operates under the same logic. Magnetomotive force, wire turns multiplied by current, drives flux through an iron core. The core restricts this flow through reluctance, the exact magnetic equivalent to resistance. Just as a wire's conductivity determines how easily electricity flows, a core's permeability defines its fundamental capacity to become magnetized. The geometries map perfectly too. Electrical current density becomes magnetic flux density, calculated as the total flux divided by the core's cross-sectional area. Because this electromagnetic duality is isomorphic, engineers calculate invisible magnetic fields inside solid iron blocks, using the exact same math used for copper wires. Calculating the magnitude of the flux solves only half the problem. We also need its physical direction inside the core. For a straight conductor, the right-hand curl rule dictates this relationship. If the thumb points with the current, fingers curl indicating the magnetic field. For wrapped transformer cores, the rule adapts. Curled fingers along the current's path means the extending thumb dictates the North Pole. Thus, wrapping geometry is critical. Wrapping wire under the core instead of over it completely reverses the generated magnetic vector. A transformer's magnetic polarity is physically hard-coded by the exact three-dimensional geometry of its copper coils. The mechanism that translates this magnetic flux back into electricity was formalized by Michael Faraday. He established that a magnetic field must be time-varying to induce an electrical current. Look at the equation for Faraday's law of electromagnetic induction. The induced electromotive force equals the number of turns, multiplied by the rate of change of the flux. The most critical variable in this formula is the plus or minus symbol. That symbol represents Lenz's law. It states that the induced EMF polarity must be oriented so that, if a current flows, the resulting secondary flux will oppose the original change in primary flux. Practically, if the primary circuit surges a flux downward through the core, the secondary circuit must actively force a new flux upward to resist it. Lenz's law dictates that every induced magnetic action triggers an equal and opposite magnetic reaction. We combine Lenz's law with the right-hand rule to determine which physical terminal on the transformer acts as the positive power source for the load. The required opposing flux dictates the current direction. That current direction then maps the exact location of the positive and negative terminals. But because terminal polarity instantly flips if a coil's physical wrapping direction changes, accurately drawing 3D coils on complex flat grid blueprints is highly inefficient. To solve this, engineers use the dot convention. We place a dot on the specific terminals across multiple isolated windings that share the exact same instantaneous positive polarity. A simple dot on a 2D electrical schematic is a dense mathematical footprint, silently encoding the 3D physical geometry and Lenz's law opposition occurring inside the iron core.